In this video, we'll be looking at various properties and laws of logarithms that we can use to help us simplify expressions or solve logarithmic equations. So we're going to start off by expressing these three properties in exponential form just to prove that they are in fact correct. So when you're taking the log of 1 with any base, that value is equal to 0. And if we convert this into exponential form, that would be a to the power of 0 equals 1. This verifies that this property is correct because anything to the power of 0 is 1. Next, if you have log a with a matching base of a, the answer is just equal to 1. And again, going into exponential form, a to the power of 1 equals a. Yes, that is true because this a here that matches this one has an invisible 1 exponent on it, so the left side and the right side match. And finally, if I have log of a to the power of x and my base is also a for my log, so these match, then the answer is just equal to the exponent on top of that a, so just x. But again, the base of the log has to match the base of that exponent. And if I convert into exponential, the base to the power of x, so a to the power of x, equals this value here. So yes, left side and right side do in fact match. Now let's go to our next one. Now in order to do this one, I'm just going to simplify the exponent slightly. So let's say instead of log x with a base of a, let's just use y instead, just to clean it up, make it a little simpler. So I'm going to convert a to the power of y equals x into logarithmic form. So I know that the base of the exponential is going to match the base of the log. I know the exponent on the exponential equation is equivalent to the answer to the log, which just leaves x right here. And now that I've done that, I'm going to go ahead and replace y with what I let y equal. I let log equal log x with a base of a. And the left side and the right side are identical, which means this property is in fact true. So if I have an exponent, so a to the power of a log, if the base of the exponent and the base of the log are the same, then your answer is just that x value. And by converting between exponential and logarithmic form, we were able to verify these properties. Next, we're going to look at three very important laws of logarithms. The first one is, if I have the log of a product, so m times n, with whatever base, I can expand that into the sum of two individual logs. So if it's multiplication here, I can turn that into log m plus log n. If it's division, then I can turn that into a subtraction of two logs. But notice, this is one log. It expands into two logs that are subtracted. And finally, if I have log m with a base of a, but that m has an exponent on top of it, that exponent can just come out in front of the log so that we're doing r times whatever this log is equivalent to. And we're going to prove that these laws are in fact true. And in order to do that, we're just going to clean something up a little bit. I'm going to replace m whenever I see it with a to the power of x. And this in logarithmic form is x is equal to log m with a base of a. And I'm going to do the same thing for n, but I'm going to say a to the power of y. And again, here's the logarithmic form. Now I did it for the first one. I took my left side, log mn with a base of a, and instead of m, I wrote a to the x. Instead of n, I wrote a to the y. And now, because these two terms are attached by multiplication, I can add these exponents. So our exponent product law. So I end up with this, a to the power of x plus y. But now, from here, I can use one of the properties from before. When the base of the log is the same as the base of the exponential part, my answer is just the exponent, x plus y. We already verified that right over here in C. So I'm using that property. And once I simplify this to just x plus y, well, I said above that x is equal to log m base a, and y is equal to log n base a. And there we go. I proved that this became this, the addition of two logs. Now let's try the same thing, but when we have division. So I'm going to start with the left side. And I'm going to start off by replacing m and n with a to the x over a to the y. And here we're using our quotient rule, which is when we have division, we can subtract our exponents. So a to the power of x minus y. And now back to that property of logs, because this base and this base match, this is just equivalent to x minus y. And now x is equivalent to log m base a, subtract log n base a from my starting statements. So left side does equal right side, QED, which QED stands for Quod Erat Demonstratum, which just is a fancy Latin way of saying that which you wanted me to demonstrate, I have demonstrated. Okay. So now, anytime that we see a single logarithm and there is division in this term, if I wanted to expand it out into subtraction, I can. Or the other way around. If I have two logs that are attached to subtraction, I can just divide these two numbers and turn it into one log expression. All right, the final law. I'm going to start with my left side again. And I'm going to replace m with a to the x. And then that's all to the power of r. And we know that when we have a power to a power, we can just multiply those. So x times r, or r times x, here we are. I'm going to write it as r times x for a reason. We'll see in a second. And again, same base, and the log and the exponent. So we're just going to be equal to r times x. But what is x equal to? It is equal to log of m with a base of a. So now, anytime that you see an expression like this, you can always take that exponent and bring it down. Or if you have a coefficient in front of the log, you can always bring it up and apply it as an exponent to that m value. And the final little formula we have is a change of base formula. If you have log a with a base of b, this can be rewritten as log a over log b. And you'll notice that these don't have bases. It's just that common base of 10. Sometimes it's a useful change of base formula to help you solve certain things or simplify certain things. So we've seen our laws, we've seen our properties, let's try to use them. The first question here is to express each of these expressions as a single logarithm. I see the addition of two logs, which means I can take the 12 and the 4 and multiply them as long as the bases are the same. Both of these logs have a base of 3, so that's good. So log base 3, and then I can multiply 12 times 4 to get log base 3 of 48. And there we are. For the next one, I have subtraction with the same base of 5, which means I'm going to divide 16 and 2. And 16 divided by 2 is 8. So we actually have log 8 with a base of 5. And finally, the last one, I notice that I have some coefficients here. So before I can unite these logs, these coefficients have to come up as exponents. So this is going to be log base 6, 9 to the power of 2, minus log base 6, 3 to the power of 3. And now I see, oh, I have subtraction, so I can unite these two logs into one by dividing 9 squared and 3 cubed. But 9 squared is just 81, and 3 cubed is just 27, so I'll write that out. And then 81 over 27 does simplify to a nice 3. So this expression that was a little longer can be simplified into just log 3 with a base of 6. Just like we can take something a little more complicated and simplify it, we can also take something more simplified and expand it out. So in our next example, we're going to write each of the logarithms in its expanded form using our sum of logarithms, because these terms here, the 5 and the 8, are attached by multiplication. So this can be expanded into log base 6 of 5 plus log base 6 of 8. Let's go to the next one. Log base 3 x squared plus log base 3 y to the negative 3. I can also take this a step further and take those exponents and bring them out front using that third log law. So when I bring the exponent down, I have 2 times log base 3 of x minus 3, because the exponent was negative, log base 3 of y. And finally, our last one, I have an exponent outside of my bracket here, which I can either distribute into my expression here, or I can bring it down in front. Honestly, the cleanest way would probably be to just distribute that exponent of 2 in. Otherwise, you would have to use some brackets to be careful that the 2 does go into both of the logs when you do expand it out into a sum of logarithms. So I will just distribute it in using my power to a power. So this is going to be x squared and y 8. So that's log base 5 of x squared plus log base 5 of y to the 8. And those exponents can just drop out front. So 2 log base 5 of x plus 8 log base 5 of y. All right, and the next one we're going to write as a difference of logs. So same idea, but because it's division of our terms, we're going to do subtraction here. So we have log base 2 of 3 subtract log base 2 of 8. And that log base 2 of 8, we can actually clean that up because we know what that's equal to. That's just equal to 3 because 2 to the power of 3 is 8. For the next one, we have log base 3. Now here in the numerator, the terms are attached by multiplication. So that I can break down into a sum of logarithms. And then the denominator, that's going to be the subtraction. So minus log base 3 of z squared. And now I can drop those exponents and bring them out in front using that third law. So I have 3 log x base 3 plus log y base 3 minus 2 log z base 3. All right, and our final one, we have log base 2 of 8 plus log base 2 of x cubed. And this time, I made our denominator have 2 terms, which means I'm going to subtract and I'm going to open up a bracket for that denominator. And the denominator is going to be log base 2 of y cubed plus log base 2 of z. Now, if you didn't want to put these brackets, you could have just gone straight to subtracting both the y and the z term because they are in the denominator. I just wanted to show this step first. So now log 8 base 2 is just equal to 3 because 2 to the power of 3 is 8. And the rest I will clean up with my logs. So 3 log x base 2 minus 3 log y base 2 plus log z base 2. Now we're going to put these laws and properties together to help us evaluate expressions that we otherwise couldn't do. So in our first example, we have log base 2 of 64 times 512. And instead of me multiplying 64 by 512, I'm going to break it down into a sum of logs. So log 64 base 2 and log 512 base 2. And now I will evaluate those logs individually and add up the answers. So I know 2 to the power of 6 is 64. So log 64 base 2 is 6. And I know 2 to the power of 9 is 512. So plus 9. And that is equal to 15. Now for the next one. Log 135 base 3 minus log 5 base 3. I don't know what the log of 135 base 3 is. That's not something part of our exponent tables that we know. So I'm going to try to simplify this to a single log and see if that helps me. Now because it's subtraction, I know I'm going to divide those values. And 135 divided by 5 is 27. So now 3 to the power of what is 27? Well, that's 3. Great. And the last one here, log of 8 to the power of 27 base 2. Now instead of me doing 8 to the power of 27, I can use my log law and bring that exponent out in front. So find log 8 base 2 and then multiply that by 27. And I know 2 to the power of 3 is 8, so there we are. And then 27 times 3 is 81. So here is the actual use of those laws to help us evaluate expressions without our calculators. Now, let's use those laws to help us solve logarithmic equations. So I have log x base 5 plus log of x plus 4 base 5 is equal to 1. These are both base 5s, and it's addition, so I can convert this into a single log expression by multiplying x and x plus 4. So I've united those logs. And once I do that, I have a single log is equal to 1. I can convert this into exponential form. So let's see what happens. 5 to the power of 1 equals x times x plus 4. And this now we can clean it up and solve the equation. So 5 to the 1 is 5. Distribute here. X squared plus 4x. This is a quadratic equation. So one side has to be equal to 0. So I'm going to bring the 5 over. And now I can factor this. So I know x times x, and then I should do 5 times negative 1. So there we are. So x can equal negative 5 or x can equal 1. Now, when you solve a logarithmic equation, your answers might not always work. And from our knowledge of log functions and what they look like, we know that log functions have vertical asymptotes, and you cannot take the log of a negative number. So we need to put restrictions on x in each of our log expressions and see what the overall restriction would be. So I'm just going to put a little number line here. And for this one here, as long as x is greater than 0, then you're good. You'll have positive numbers to take the log of. But for the other one, we have x plus 4. In order for that bracket to be positive, x has to be greater than -4, and then you're good. Now, the restriction that will satisfy both of those logs and this equation in general is the portion that overlaps. And this is the overlapping restriction, which is that x is greater than 0. Okay, because if I'm greater than 0, then this is good with me, and this is good with me. Both of those values would be positive. But if I put something here between -4 and 0, although this one would be okay, this would have a negative value, which I can't take the log of. So with this restriction in mind, x equals -5 does not fit within that domain. So my only answer here is x equals 1. Okay, let's try another one. I have log of 3x plus 2 base 2 minus log of x minus 2 base 2 equals 3. I have subtraction this time, so that's going to be division when I combine my logs. Here we are. And now we can convert to exponential form. So 2 to the power of 3 equals that fraction. And 2 to the power of 3 is 8. And now I have a rational expression equals a value. So I'll put that 8 over 1. And now I'll just cross multiply. So 8 times x minus 2. Make sure both the x and the 2 are multiplied by 8. And then equals 3x plus 2. Now I'll just bring the 3x over and the 16 over to the other side so that I have 5x equals 18. And when I divide both sides by 5, I get 18 over 5. And that's my only answer here, but I have to check my restriction to make sure that this works. So my restriction on my first log is that x has to be greater than -2 over 3. So I'm just solving that bracket, setting it equal to 0 and isolating for x. So I'm going to put that roughly on a number line. So let's say 0 is here, -2/3 might be here, and this is what I want. Actually, let me change the color. This is the part that I want, so -2/3. For my other one, my restriction would be that x has to be greater than 2. If we're greater than 2, then that portion will be positive. So again, number line 2, let's say it's somewhere over here. And here's my restriction. The overlapping restriction is about the 2. X has to be greater than 2 for this equation. And 18 over 5 is bigger than 3. So this works. That is good. So here we are solving logarithmic equations. We are using our log laws to take multiple logs and turn them into a single expression. So for that addition expression, I multiplied. For the subtraction, I divided. And once I turned it into a single logarithm, I could convert into exponential form, and then I'm back to basic algebra skills that I should have. All right. The next one, we're just going to simplify the logarithmic expression and then state any restrictions. So first thing, I see my subtraction here, which means when I combine them, I will have division. So log, and then I'm going to have x squared minus x over 12 over x squared minus 4x minus 21. Now, when I'm seeing this, I see two quadratics in the numerator and denominator, so I'm thinking we should factor here. So in my numerator, I'm going to have x minus 4 and x plus 3. And in the denominator, I'm going to have x minus 7 and x plus 3. And the x plus 3's cancel out. So my simplified logarithmic expression is the log of x minus 4 over x minus 7. Now, I need my restriction here. And I need each of these sections here to be greater than 0, but these are parabolas. So I'm going to create a number line here and think about what the parabola looks like. And I am going to use my factored form. So I'm going to start with the numerator, where my brackets were x minus 4 and x plus 3. So let's just say this is 0. And I'm going to make 2 of these zeros here. So the zeros on my numerator are 4 and negative 3. So here we are. Those are the zeros. Pretend I'm graphing a parabola. Those are the zeros, and this parabola opens up because the coefficient of x squared is positive. So here's the parabola. Now I need that parabola, that quadratic equation, to be greater than 0. We're greater than 0 from 4 onwards, and from negative 3, and even more negative. So if I'm greater than 4 or less than negative 3, this parabola will be positive, because the negative part I do not want. Now I'm going to do the same thing for my denominator and find those overlapping regions. Now for the denominator, one of my zeros is also negative 3, and the other one is at 7. Let's pretend 7 is here. And this parabola also opens up, so here we are. And again, I want the positive region. So from 7 onwards, and from negative 3, more negative. And now where's the overlap? Well, these ones are identical, so one of my restrictions for sure is that x is less than negative 3. That way I'll have a positive value. And the other part overlaps only when we're greater than 7. So x is greater than 7. If I satisfy one of these conditions, one of these restrictions, I will have a positive number to take the log of. And that is the goal here, because again, the restrictions correspond to the vertical asymptotes of your logarithmic function. Let's try another one. Again, I have subtraction, and this time I have base 5. And actually, I notice this coefficient that will become an exponent. So I'll have x squared minus 9 in the numerator, and in the denominator, I'll have x plus 3 squared. I'm just going to do 2 steps in one. And now my numerator, of course, is a difference of squares. So I should factor that. And something does cancel out. One set of x plus 3's. So we have x minus 3 in the numerator and x plus 3 in the denominator. Now my restrictions are going to come from the original expression. So I need to look at a number line for x squared minus 9. So let me create a number line 2, one for the numerator, one for the denominator. And for x squared minus 9, we know the zeros are at 3 and negative 3. And this parabola, again, opens up. So I'm going to draw like this. And I want the positive versions. So this arm is in the positive region, so this is a good interval, and this arm is in the positive region, so less than negative 3. For the other one, I'm just looking at x plus 3. Okay, and for x plus 3, as long as we're greater than negative 3, we're good. Then that portion will be a positive number. Now, where's the overlap? No overlap with that. The only overlap is right here. X has to be greater than 3. And as long as you're greater than 3, both of these logs that you have to take will be positive. And that was the goal. All right, next style of question. Evaluating using the change of base formula. Okay, well, this is just the log of 5 over the log of that original base, so 4. There it is. The next one, the log of 8 over 9 over the log of 5. And the last one, I mean, this one's a little silly to do because the base is 10. And if I do my change of base, I have log 3 over log 10. But log 10 is just equal to 1 because the base of that log is also 10. So it just takes me back to 3. So a little silly to do the change of base formula there, but there it is in action. All right. Our last example here is expressing each of these expressions as a single logarithm. All right. So we have log 5 over log 8. This is me undoing the change of base formula. So the denominator would represent the base, so the 8, and then the 5 is there. So log 5 base 8. For the next one, again, the denominator gives me my base, so log base c, and then the a minus 2b. Now it's a single logarithm. And for c, I'm going to do my change of base for each one. And you might be asking, how is this going to turn into a single expression? Well, you'll see. So the first bracket will be log b over log a times log c over log b times log d over log c and times log x over log d. And now you'll notice the log b's cancel out, the c's, the d's, and all you're left with is log x over log a, and that can be written as a single logarithm log base a of x. And there we are. And in this chart here are just a summary of the properties that we've looked at, plus maybe a few extras, and then some situations where brackets can be avoided and some where it cannot. So when you have this multiplication or division, if you avoid the brackets, it's fine. It still implies the same thing. So even here, those are equivalent. Or here, log A, log B, it's implied that there's multiplication. Or log A, we have brackets here, times B, which you'll notice is different from this here. To avoid confusion here, so that you don't need brackets, if you put the B out in front, then problem solved. Okay, and then this is equivalent to this because of the log law that we do know. And here, this is acceptable, okay, but although this does mean that the b is not part of the log, this might just look a little better, look less ambiguous. So b plus log a. So this section here, if you read through, it's just a better ways to communicate things to avoid confusion and what things are equivalent, whether brackets are there or not. Now it's the bottom ones that I really want to emphasize here. Here brackets are super important. If I want this to be a plus b and I'm taking the log of that, brackets are crucial, because if you don't have brackets, this is just find the log of a, and then after you do that, then add b. So these are not equivalent. In this question here, okay, you'll see the importance of brackets. I'm taking the log of a times another log. I can take this a and bring it up into the exponent, so now I'm taking the log of this log. Over here, when you have brackets and then an exponent on the outside, this is not the log law where you can bring the b out in front, because this b is not directly attached to a. This is the logarithm all to the power of b. So these are not equivalent. Okay, and finally, log of negative x is not equivalent to log minus x, because this looks like you're doing log subtract x, and log on its own is not actually a value. So this is just unacceptable altogether. Okay, and finally, if you see log squared x, that just means take the log of x and then raise that to the power of 2. And that's it for our laws of logarithms. Again, we saw places where we were able to use our logarithmic laws to solve equations like a number 5, or to manipulate logarithms so that we can evaluate them better.